Here are the solutions to the Further Mathematics Written Examination 2 2019 for VCE. We are going to start with Section A, Core, Data Analysis. Question 1. Table 1 shows the day number and the minimum temperature in degrees Celsius for 15 consecutive days in May 2017. In Part A, we are asked which of the two variables in this data set is an ordinal variable. An ordinal variable represents order. Even if we have numbers, these numbers don't have any other significance but to represent the order in which the data was collected. For this reason, the ordinal variable in this question is day number. The incomplete ordered stem plot below has been constructed using the data values for days 1 to 10. In Part B, we are asked to complete the stem plot above by adding the data values for days 11 to 15. From the table, the minimum temperature on day 11 was 7.5 degrees Celsius. Therefore, we are going to write a 5 in line with the 7 in the stem. On day 12, the minimum temperature was 8 degrees Celsius. Therefore, we are going to write a 0 in line with the 8 in the stem. On day 13, the minimum temperature was 8.6 degrees Celsius, so we are going to write a 6 in line with the 8 in the stem. On day 14, the minimum temperature was 9.8 degrees Celsius. Therefore, we are going to write an 8 in line with the 9 in the stem. And finally, on day 15, the minimum temperature was 7.7 degrees Celsius. Therefore, we are going to write a 7 in line with the 7 in the stem. From the 2019 VCE examination report, some students entered only the values for day 11 and day 15 rather than the 5 days from day 11 to day 15. Part C. The ordered stem plot below shows the maximum temperature in degrees Celsius for the same 15 days. Use this stem plot to determine, in Part I, the value of the first quartile Q1. First of all, let's determine the median, which is the value in the middle, that is the 8th score, which is 13.7 degrees Celsius, and Q1 is the value in the middle of the first half set of data, which is the 4th score. So Q1 is equal to 12.2 degrees Celsius. In Part 2I, we are asked to calculate the percentage of days with a maximum temperature higher than 15.3 degrees Celsius. From the stem plot, we can see that there are 3 days with a maximum temperature higher than 15.3 degrees Celsius. That is 15.5, 15.6, and 16 degrees Celsius. 3 out of 15 times 100, we multiply by 100 to find the percentage, equals 20%. Question 2. The parallel box plots below show the maximum daily temperature and minimum daily temperature in degrees Celsius for 30 days in November 2017. Part A. Use the information in the box plots to complete the following sentences. For November 2017, in Part I, we are asked to calculate the interquartile range for the minimum daily temperature. From the box plot for the minimum daily temperature, we can see that Q1 equals 12 and Q3 equals 17. Therefore, IQR equals 17 minus 12, which is 5 degrees Celsius. In Part 2I, we are asked to determine by how many degrees the median value for maximum daily temperature is higher than the median value for the minimum daily temperature. From the first box plot, we can see that the median for the maximum daily temperature is 25 degrees Celsius And from the second box plot, the median value for the minimum daily temperature is 15 degrees. 25 minus 15 equals 10 degrees Celsius. In part 3I, we are asked to determine the number of days on which the maximum daily temperature was less than the median value for the minimum daily temperature. We draw a vertical line from the median for the minimum daily temperature up until it crosses the other box plot, and we can see that there is only one day with the maximum daily temperature less than this value. So the answer is 1 day. Part B. The temperature difference between the minimum daily temperature and the maximum daily temperature in November 2017 at this location is approximately normally distributed, with a mean of 9.4 degrees Celsius and a standard deviation of 3.2 degrees Celsius. We are asked to determine the number of days in November 2017 for which this temperature difference is expected to be greater than 9.4 degrees Celsius. We know that there are 30 days in November. Since 9.4 degrees Celsius is the mean, then 50% of the days will have a temperature difference greater than 9.4 degrees Celsius. 50% of 30 days is equal to 15 days. Question 3. The 5-number summary for the distribution of minimum daily temperature for the months of February, May, and July in 2017 is shown in Table 2. The associated box plots are shown below the table. Explain why the information given above supports the contention that minimum daily temperature is associated with the month. Refer to the values of an appropriate statistic in your response. The association is shown by the decrease in the median value from 10.9 degrees Celsius in February to 7.5 degrees Celsius in May and to 5 degrees Celsius in July. Another statistic that could be used for this answer is the IQR for the 3 months. Question 4. The relative humidity in percentage at 9 a.m. and 3 p.m. on 14 days in November 2017 is shown in Table 3 below. A least squares line is to be fitted to the data with the aim of predicting the relative humidity at 3 p.m. from the relative humidity at 9 a.m. Part A. Name the explanatory variable. The explanatory variable is the humidity at 9 a.m. because we predict the relative humidity at 3 p.m. from the relative humidity at 9 a.m. Part B. Determine the values of the intercept and the slope of this least squares line. Round both values to 3 significant figures and write them in the appropriate boxes provided. First of all, we need to enter the data in a spreadsheet on available CAS technology. Notice that the explanatory variable is in the first column, labeled 9 because it's 9 a.m., and the second column labeled 3 for 3 p.m., and this is the response variable. Then from menu, use 4 statistics, 1 stat calculations, and 4 linear regression A plus BX. Choose 9 in the X list and 3 in the Y list. From the following screen, we can see that the intercept A is negative 1.26 to 3 significant figures, and the slope is 0.765, again to 3 significant figures. Part C. Determine the value of the correlation coefficient for this data set. Round your answer to 3 decimal places. From the same screen, we can see that R, the correlation coefficient, is 0.871, correct to 3 decimal places. Question 5. The scatter plot below shows the atmospheric pressure in hectopascals at 3 p.m. plotted against the atmospheric pressure in hectopascals at 9 a.m. for 23 days in November 2017 at a particular weather station. A least squares line has been fitted to the scatter plot as shown. The equation of this line is given below. Part A. Interpret the slope of this least squares line in terms of the atmospheric pressure at this weather station at 9 a.m. and at 3 p.m. The slope is 0.8894, which means that on average the pressure at 3 p.m. increases by 0.8894 hectopascals per every increase of 1 hectopascal of pressure at 9 p.m. Part B. Use the equation of the least squares line to predict the atmospheric pressure at 3 p.m. when the atmospheric pressure at 9 a.m. is 1025 hectopascals. Round your answer to the nearest whole number. All we have to do here is substitute 1025 for pressure at 9 a.m. Therefore, the pressure of 3 p.m. is predicted to be 1023 hectopascals. Part C. Is the prediction made in Part B an example of extrapolation or interpolation? This is an interpolation because the pressure 1025 hectopascals is within the range of data. Part D. Determine the residual when the atmospheric pressure at 9 a.m. is 1013 hectopascals. Round your answer to the nearest whole number. We know that the residual is equal to the actual value minus the predicted value. So for a pressure of 1013 hectopascals at 9 a.m., we go up until we find the data point, and then we go across, and we read from the graph 1015 hectopascals, the pressure at 3 p.m. So this is the actual value. Now we are going to use the equation given to calculate the predicted value. So we are going to substitute 1013 hectopascals for pressure at 9 a.m. And this gives us a pressure of 3 p.m., the predicted value, as 1012.36. The difference is going to be 2.64, which is approximately equal to 3 as required to the nearest whole number. Part E. The mean and the standard deviation of pressure at 9 a.m. and pressure at 3 p.m. for these 23 days are shown in Table 4. Part I. Use the equation of the least squares line and the information in Table 4 to show that the correlation coefficient for this data, rounded to 3 decimal places, is R equals 0.966. We are going to use the formula for the slope, which is equal to the correlation coefficient R times the standard deviation for pressure at 3 p.m. divided by the standard deviation for pressure at 9 a.m. We substitute the values known, and by solving this equation, we end up with R equals approximately 0.966 to 3 decimal places. Part 2I. What percentage of the variation in pressure at 3 p.m. is explained by the variation in pressure at 9 a.m.? Round your answer to 1 decimal place. For this, we are going to need the coefficient of determination, which is R squared. 0.966 all squared gives us 0.93257. We multiply by 100 to find the percentage, so that is 93.3%, correct to 1 decimal place. Part F. The residual plot associated with the least squares line is shown below. Part I. The residual plot above can be used to test one of the assumptions about the nature of the association between the atmospheric pressure at 3 p.m. and the atmospheric pressure at 9 a.m. What is this assumption? The assumption we make is that there is a linear association between the two variables. Part 2i. The residual plot above does not support this assumption. Explain why. The residuals in this graph have a clear pattern. For a linear association, we need no pattern. We need the points to be random. Question 6. The total rainfall in millimeters for each of the 4 seasons in 2015 and 2016 is shown in Table 5 below. Part A. The seasonal index for winter is shown in Table 6 below. Use the values in Table 5 to find the seasonal indices for summer, autumn, and spring. Write your answers in Table 6, rounded to 2 decimal places. We first need to calculate the average for the 8 seasons. And that is 155. Now we are going to calculate the average for summer and then the seasonal index for summer, which is 0.89 corrected to decimal places. We now calculate the average for autumn and the seasonal index for autumn, which is 1 corrected to decimal places, and the average for spring and the seasonal index for spring, which is 0.70 corrected to decimal places. Part B. The total rainfall for each of the 4 seasons in 2017 is shown in Table 7 below. Use the appropriate seasonal index from Table 6 to deseasonalize the total rainfall for winter in 2017. Round your answer to the nearest whole number. The deseasonalized value for winter is equal to the actual value for winter divided by the seasonal index for winter. Correct to the nearest whole number, this is 186.